Welcome to the third season, Earth is Our Home, in which Dr. Tom Blaine is going to be talking about the global climate change and give a 2023 update. So stay tuned. Welcome to the third season of Earth is Our Home with Dr. Thomas Blaine. Dr. Thomas Blaine is an associate professor with the Ohio State University Extension Program. Today, Tom is going to be looking at global climate change, a 2023 update. Tom, it's really great talking with you. It's hard to believe that we're in our third season.
It's been great, Patrick. I really enjoyed it. We started in the spring of 2021, and, we've covered so many dimensions of global warming / climate change. We've done a lot of programs on how the global climate engine works and how it's changing now as a result of human activities. We did a special 3-part series last year, second season, on the war in Ukraine. And that's because Earth is Our Home is really about existential threats to humans, things that could drive us out of existence. And global warming, we are running that risk eventually that it will do that. To start the third season is catch everybody up on where we're standing on global warming, where the trends are, and everything like that. So we're going to go back to that basic for the first few episodes, at least, of the season. Okay, so today, first program of season 3, Earth is Our Home. We're doing climate change as it stands in early 2023. And it's an update. So what I want to tell you is that for the past 10,000 years, that is a pretty long time. That's since the end of the last ice age. Carbon dioxide concentrations have varied in a very narrow range, around 280 parts per million. That means if you grabbed 1 million particles out of the atmosphere, molecules, atoms, you'd have some oxygen, you would have nitrogen, you'd have 1 million particles, 280 of those would be carbon dioxide molecules. That was the case for virtually 10,000 years. That was the case for about 10,000 years. But scientists began studying atmospheric physics, especially in the middle of the 1800s, and began to study which gases in the atmosphere affect the trapping of heat to warm the planet. And they found out that carbon dioxide is one such gas. It's called a greenhouse gas because when you have CO2 and you try to pass heat through it, some of the heat gets blocked. That's really important because what that means is the CO2 in the atmosphere contributes to a warming of the planet. If we had no CO2 in the atmosphere, if that 280 went down near zero, not only would all the plants die because they take it in and respire oxygen. We're the opposite. Animals take in oxygen and produce CO2. But if that CO2 went down near zero, the temperature of the Earth would plummet and the entire planet would freeze. So even though 280 parts per million doesn't sound like a lot, just from there down to zero, we would have ice essentially all the way to the equator. it would be snowball Earth. Now, during the last ice age, here's a globe way it looked in the ice age about 25,000 years ago when we reached the glacial max. CO2 concentrations were 180 parts per million. That's 180. So keep that number in mind. 180 corresponded with the CO2 concentration during the middle of the last ice age. And then we naturally went up to 280. And here we are 10,000 years ago when we reached 280. And you can see most of the ice is gone. That's given us the Earth that prevailed until just a couple of hundred years ago. The average Earth temperature was 10 degrees colder than it is now during the last ice age. 10 degrees Fahrenheit. That's the thing. It doesn't, 10 degrees might not sound like a lot, but 10 degrees, is the difference between that Earth, and you can see Ohio's under ice. Much of the northern United States is under ice. Tennessee and Oklahoma were like an Arctic tundra. And there you are at 280. So that's just 100 parts per million difference. Now, the ending of the ice age was not caused by that CO2 change, though. The ending of the ice age was caused mainly by changes in Earth's orbit around the sun. The Earth's orbit around the sun goes through regular cycles. The tilt changes, the eccentricity of the orbit. It's not a circular orbit. That changes. The time of year when we're closest to the sun changes. And this produces 100,000 year cycles that cause the ice age. Ice ages to come and go. Nevertheless, since the Industrial Revolution about 200 years ago, CO2 concentrations have increased by 50%. So that 280 that existed for about 10,000 years is now 420. So remember, 180 during the Ice Age, it's 180 parts per million. Very narrow range it varied, almost no variation for the better part of 80,000 years or so. Then it went to 280 and very small, 5 to 10, 15 parts per million variation. Carbon dioxide is normally very stable for thousands of years. However, we burn a lot of coal, oil, natural gas. We've done this since we began to industrialize, and now we're at 420 parts per million. That's a 50% gain, and it's a much bigger gain than the natural gain that took thousands of years. So when people say, well, there's natural variation, there is natural variation, but not like the kind of variation caused by humans. This increase in CO2 up to 420 parts per million has enhanced the greenhouse effect. So as this has happened, as we've gone from 280 parts per million to 420 parts per million, temperatures increased by about 1.8 degrees Fahrenheit. And there's the surface temperatures. This goes back to about 1880. And the zero on there is the baseline temperature. You can see it running across the middle. And you can see the recent temperatures are up there between about 1.44 and close to 1.8. But the total increase has been about 1.8 degrees Fahrenheit.
Our instruments of today are more accurate than they were, say, 20, 30, 40 years ago. Does that play into some effect when it comes to getting information about the temperature changes?
Okay. I have a little bit of skepticism about this surface data set too, but I don't agree with you that a thermometer that we used 100 years ago, you hang a thermometer, like my great grandmother might have had in her house. I think that thermometer was just as accurate as the ones we have today. So I don't necessarily agree with you that the thermometers are more accurate today. These are pretty much old school measurement techniques, but there are some other potential problems with this data set that don't relate to that, like whether or not there's been development close to where the thermometers are located that could cause an elevation in the temperature right around that vicinity. That's not really a global type phenomenon. It's just a localized microclimate. That's the main critique of this data set. And so I'm always a little cautious with this data set, which is why I go and look at another one that we're going to check this out in just a second. But the current warming trend is about 1/4 degree Fahrenheit per decade. So if this trend continues, the Earth will be another degree warmer by about 2060 than currently. Keep in mind, we've gone up 1.8 degrees in over 100 years. And now we're likely to go up by about 1 degree Fahrenheit in the next 40 years, which would be 2.8 degrees warmer than the pre-industrial level. But it's difficult to estimate with precision. And that's what I think you were asking a little bit when you mentioned that. It's difficult to estimate even current temperatures globally. And then when you try to forecast out, it's difficult to estimate what that temperature increase will be. We know CO2 traps heat. Scientists proved that in the 1850s. So escaping heat trying to escape from Earth up into space gets trapped by this additional CO2 and contributes to global warming. The expected 1 degree increase is keep in mind it's an estimate, but there are potential changes, feedbacks that could very well amplify the warming. So we're raising temperatures, but we're also raising risks. So, but anyway, before we get back to that, I wanted to tell you when I get a little bit nervous about the older temperatures versus the newer temperatures on the land-based. And I know you're maybe skeptical that some of the old-time thermometers weren't that accurate. Maybe that's true. I tend to think they were, but then I pointed out another problem with the land-based data set, that sometimes where the temperature instruments are located, there might have been warming right around there where you had development. And so that's why I always turn to this data set. This is satellite-based temperature. It measures the temperature of the entire lower troposphere. So it's not prone to any of those. It's same technology. The only downside of this is it only goes back to 1979. However, 1979 has been well over 40 years, about 45 years now, and 44 years or so. And as a result, we've got a trend. So we can follow this trend that's not corrupted by antiquated instruments. It's not corrupted by anything local. It's the entire lower troposphere. And so when I have problems, like you mentioned with the land-based, and water ocean-based temperature instruments, I go ahead and look at this satellite. And as you can see to the left, most of the data is below the axis. To the right, most of it's above the axis. This shows about 0.6 of a degree warming centigrade, which is about a degree warming just in the past 40 years. So this removes any doubt that I have about the magnitude of this warming. Okay, so now we're looking at what happens when we get another 1 degree temperature rise, let's say between now and 2060. What the problem is with that, because a 1 degree temperature rise from where we are now in the early 2020s would cause some problems on planet Earth. Again, I know it doesn't sound like much, but remember, it was only 10 degrees difference at the last ice age. We've already gone up 1.8, so going up 2.8 is significant. But the real problem is that could cause feedbacks. So we get more snow and ice melt, and that in turn adds to warming, because the melting of permafrost releases methane, which is CH4, which is another potent greenhouse gas. And if we release a lot of methane from the permafrost or from frozen parts at the bottom of the Arctic Ocean, we could contribute quite a lot to this warming, especially in the Arctic. Now, as we've noted before, what separates the current climate from a hothouse where you have Minnesota and Wisconsin with climates like the Amazon, that's the hothouse. 100 million years ago, when dinosaurs roamed the earth, you had tropical type weather conditions all over the globe. What has prevented that now are the polar regions, which serve as air conditioners to the planet. So it's about 17 degrees hotter than now when the dinosaurs roamed the earth. And these conditions were caused by a lack of cooling at the poles, because warm ocean waters from the tropics flowed right up over the poles unimpeded. Okay. But between 10 and 30 million years ago, that flow was shut off. Eurasia, North America, and Greenland prevent any equatorial waters from getting anywhere near the North Pole. So the Arctic Ocean freezes. It serves to cool the planet. In the southern hemisphere, Antarctica straddles the pole, the continent that prevents warm water from getting anywhere near the South Pole. And so we've got air conditioning that prevents our Earth from being like what the dinosaurs had. And this air conditioned Earth is what we humans have evolved in. At least 10 million years of this. And the first upright walking apes, our ancestors that first walked upright, came along about 6 million years ago. They evolved in this ice house that we've got now. This is the only Earth that not only Homo sapiens knows, but any of the genus Homo, any of the upright walking apes. And we've also configured the Earth to meet our wants and to give us the lifestyle we have. Now, return to the hothouse. If we go ahead and warm, and it triggers these feedbacks with methane and other kinds of feedbacks that could cause a warming of, say, 5, 6, 7 degrees Fahrenheit. No, it won't destroy Earth. We're not talking about destroying Earth, but it will cause mass extinctions and an end to our civilization, and possibly even an end to our species. as agriculture collapses and the planet becomes essentially uninhabitable for current species, because no species on Earth has evolved in a hothouse. For example, a 10-degree spike in temperatures 252 million years ago caused the Permian extinction, 10-degree increase. Over 90% of species in the seas went extinct, and about 80% of species on land. This event is known as the Great Dying and is one of 5 major extinctions during the current eon. I can't say whether the current warming will lead to a runaway feedback, may very well not. But a return to the hothouse would bring about Earth's 6th major extinction. It already has a name because we're losing about 200 species a day. And the name of this new extinction is called the Anthropocene, means caused by humans, as opposed to the Permian extinction, which was a natural event. And I'm not talking about the kind of hothouse the dinosaurs had. It's not going to do that. But even a 5 to 7 degree Fahrenheit increase could cause this collapse. And every degree we warm the planet, we increase the risk that that will happen. And so it's a question of risk. We can't say for sure. I can't tell you for sure. My best estimate was a degree Fahrenheit by 2060. What that will cause in turn, in terms of feedbacks with methane and the melting of ice and snow at the poles, causing them to warm. It's a possibility. And that's why I say we're running a risk. This is my contact information. If you have comments, you can feel free to put them down below the video or contact me if you'd like some more information or like for me to do an episode on some other aspect of global climate change. You can go ahead and click like on the video if you want, and then write on the comments another aspect of climate change you'd like to see me address. Thanks a lot.
Hey, we're talking with Dr. Thomas Blaine. He's an associate professor with the Ohio State University. And I've always found Tom to be willing to answer any questions. If you can email him or give him a phone call, he will do his best. Tom, good show. I better understand climate change and the update. Thank you.
Thank you, Patrick.